Hello, my name is Robert Feranek. I'm from Federal Academy, and in this video we are going to speak about schematic checking. I decided to create this video because I've seen many schematics with mistakes which can be very easily fixed, prevented, and found if schematic is checked properly. So I'm going to show you how we do it at Federal Academy, and I really hope you will find it useful and you will use it in your future projects to make them right at the first time. In this video we will be working with our OpenRex project, and because I know a lot of people use microcontrollers in their designs, I'm going to show you how to check a microcontroller page of this whole project. This is the microcontroller page. What I always use in schematic checking is Navigator. You can find it here, Design Compiler Navigator. It's this special panel. Before you start using this panel, you may need to compile your project because sometimes this can be empty. You need to go here, right click and compile. Once it is compiled, then in the Navigator you will see 4 small windows. Here you can see all the pages in your schematic. When you click on a particular page, you will see all the components on the page. You will see also all the nets on the page. When you select a net, you will see all the pins where this net is connected. What is also useful, by default Altium doesn't check this show graph. I'm going to show you what is the feature about. If I select this net, it looks like this. If I check the show graph, I checked it. When I select it now, you will see there these red dots and these red lines. It's very useful. It makes the connection more visible. So I always use the show graph enabled or checked. Now, very important tip. Never ever order the signals in this window. It's because Altium can't remember how you set the ordering, and for example, if you switch off and switch on Altium, you will lose the track of the signals which you have checked and which you still need to check. So just leave it as it is, never click here. Okay. What I also need to mention before we start the checking is that the schematic which we are using in this video is not finished, and it's because I would like to show you some mistakes which we will find during the checking. It was enough talking, let's do some checking. Double click on the processor page and select the first net which is in this list here. Click on the pins where it is connected. This is very simple net, there is not really much to check, and it's connected right. I close it and I go and move to the other net. This one is going to be a little bit more complicated. What do we need to check here? Transistor connection, that's fine. Resistor connection, that's fine. Microcontroller connection. This is what we have to check. First, what I would like to see how they connected this pin in their reference schematic. So open the reference schematic of the evaluation board of this microcontroller. It's not exactly this microcontroller and it's a different footprint, but this is the reference schematic which we can use. And here is the pin. So let's select this net and let's have a look where it is connected. It's it's only connected here. I can see it. So only to a expansion connector. It's not really important pin. It's not used for any programming or firmware update, debugging, or these things. It does not require any special pull up, pull down to make this microcontroller work, but it may require something in the connection which is used in our schematic. So we still need to have a look what is the exact feature of this pin and be sure it is connected correctly. So have a look into datasheet. This is the datasheet. It's important always check what is the after reset condition. So after reset, this pin is set as input and it has internal pull up. It's fine as we have it now. And this is very important. In general purpose digital input output pin, a low level on this pin during reset starts the ISP command handler. We will be using ISP to update firmware inside the microcontroller. So we have to be able to set low level on this pin. Let's go back to our schematic. And we need to follow where the pin is connected. It goes to a processor, and in the processor we can use this GPIO to set low level on the pin, so the connection is correct. What we also need to check is what is the initial state after reset state of this pin, if it's input, output, if there is pull up or pull down. And also we need to check if the level on this pin is 3.3 volts. That's what we need for the microcontroller. You may think it is always 3.3 volts. It is not. This processor is quite complex and there are several power blocks. And some pins, they can have, for example, 2.5 volt level. Some pins can have 3.3 volt level. So we need to be sure here is 3.3 volt level. I open datasheet of this processor and I will look for B21 pin. This is B21 pin. This is the datasheet. And here you can see out of reset condition, definition if it's input or output, if there is pull up, pull down, or if there is high or low, and this is the power group. This is the pin which is used to power the GPIO. And this is important for us. B21. After reset, it said it is input, it has pull up 100K, that's fine, and it's connected to the power which is connected to the pin NVCC SD1. I go to our schematic, to processor power page. This is the processor power block, and I will find NVCC SD1 pin. It's here, NVCC SD1, and it's connected to 3.3 volts. So the level on the pin will be 3.3 volts. It looks okay. Connected to GPIO, we can control low and high on this pin, and the level is 3.3. In the reference schematic there is nothing special, so I'm happy with connection of this net. What you just learned, it's very important, because this is exactly the way how you can create large, big, huge schematics which will work. You need to go through every pin, every net in your schematic, and if you feel confident that this small pin and this small net is connected correctly, then once you finish checking the whole schematic, you will feel pretty confident that your schematic is correct. We can now move to the next net. I click here and we are going to browse it. This is USB. For this kind of signal, I always look if the whole signal is connected to a positive or negative net. Because a lot of mistakes happen that you somehow swap negative and positive net names or ports, and then the connection is wrong. So first what I look for is positive P, positive P, positive P, where it continues. It goes here and it's connected to positive P, and it's connected to positive, positive, and it also continues here, positive, positive, and to be able to see where this signal is connected, I need to click here on the top of the hierarchy and have a look. Positive, and it goes here and it's positive. Okay, good. Go back. Can you see what is this connection about? Our USB from the microcontroller, based on these optional resistors which are here, can be connected to the USB hub, and through the USB hub it can go and be connected to the processor, or it can be routed to the header on the board. Okay, let's go back to our page and to our signal. We need to check now what? The reference schematic. So USB P signal. Here's the reference schematic. Oops. This is the USB P signal. It is connected to 33 ohm resistor. 33 ohm resistor, we have it there. Good. And also it goes somewhere here. And it continues here. Uh-oh! We have nothing like this in our schematic. Maybe we found something. It's very important now, you need to check what is this circuit about, if you would like to implement it or not. In the final schematic of the OpenRX, you will see we decided to implement this circuit. So we found first mistake. Let's go back to our schematic. And we also need to check the datasheet. USB P. Oops. How they call it exactly? DP. It's very important. You also check the schematic symbol, and especially you check the pin names in your schematic symbol. They need to be correct, because you can see during the checking we use the net names to check if the pin is connected correctly. It's USB bidirectional D plus line, nothing special about it. So this connection looks okay. We can move to the next signal. You know exactly what to do with the next signal. Click there, have a look. M, that's minus, that's negative. So negative, negative, negative. Negative, minus, negative, negative, negative. And the pins. Let's go to reference schematic minus 33 ohm resistor, and it goes directly to the connector. It's fine. Have a look into datasheet minus USB bidirectional D minus line. That's fine. I'm sure you got the point. So we can now move a little bit more quickly. I'm not going to go into reference schematic and into datasheet for every single pin in this schematic page, because the video would take a long time. But I know which of the pins are important, so I will then tell you. The next pin, we already checked this one. And we also checked this one. Touch screen. In this connection, we decided to use these analog input pins for a touchscreen interface, or to support. One of the options will be touchscreen interface. Again, have a look. Y minus, and it continues as Y minus. That's fine. There is a bead, capacitor, and it connects to a connector. Here is another thing what we could improve. What do you think? Because it's a touchscreen interface, it may be useful to consider to put there ESD protection. So you can make a note, put ESD protection on the touchscreen interface. Usually I just put here a text or something. I'm not going to do it now because it always then requires recompile the schematic. But you can just copy and paste this NF, or I will show you, so you know exactly how to do it. You need to click on this editor. Control C, add ESD on touch. Okay, that's a note for someone else, for example for Martin, who will be updating the schematic. Now when I click here, it's going to recompile the schematic because we made a change. And we can continue. Very similar to epsilon or y minus. So I just go here very quickly. I go here very quickly. Don't forget, you should be checking datasheet, you should be checking reference schematic for every pin which we are going through. This is fine. Crystal. It connects to 12 MHz crystal and 18 picofarad capacitor. It connects to 12 MHz crystal and 18 picofarads. Again, don't forget this is different footprint, so here are different pin numbers, but the connection should be like we can see here. Okay. Possibly have a look into datasheet. In datasheet, they many times they explain what kind of capacitor value you should use with a specific crystal. I found the crystal section in the datasheet, so you can see how they explain it. This is the crystal connection, and in this table, if we use 12 MHz crystal with load capacitance CL 10 picofarads, then we need to use 18 picofarad capacitors connected to ground. However, if you use a crystal with load capacitance CL 20 picofarads, you will need to use 39 picofarad capacitors. These. Instead of 18 picofarads, you would use 39 picofarad capacitors. Reset. Reset is one of the most important signals in microcontroller and processor boards. So you need to be pretty sure it's connected correctly. Our reset can have two different sources. This one is connected to processor. So if it's needed, we can reset the microcontroller through this A21 pin. What we need to check about the A21 pin, do you remember? We need to check what will be the default after reset condition, and also what will be the level on this A21 pin. And the other source is the main board reset. This is main board reset. I will just browse through all the other pages so I see where it is connected. It connects to all the other chips on the board. Okay. Next. Uh-oh, I see another possible problem. Can you see it too? we may be mixing different power rails. The microcontroller can be powered from 3.3 volt voltage or 3.3 LDO voltage. However, here we are using 3.0 always voltage. And this is the situation when you need to start to think about the circuit which is used inside the chip. You need to know what is inside the chip. Only looking at the schematic, that's not enough. So do you know what is inside this chip? What is usually a pin connection inside the microcontrollers? There is ESD protection. And usually this is the way how they do ESD protection. Inside the chip you have two diodes. One is connected to the power pins and one is connected to ground. So if you are mixing different power rails, what may happen is there may be some currents flowing through these diodes which are inside the chip. The second thing is many times you have pull-ups and pull-downs inside the chips. So what we need to do, we need to have a look what is inside the reset pin. This is the connection from the datasheet. Many times in the datasheet you will find special section also for the reset with recommended circuit and with the circuit inside the chip. So this is the pin, here is the ESD, what we were speaking about, and is something else. So there is also possible internal pull-up. Again, the way how you can connect different power rails together. You don't want to flow currents through this internal pull-up or through this ESD diode. So what we will do, we will replace this power with something else. The safe way will be probably use this one, which is here. GPIO pin. And even now I can see it's going to be something special because there is pull up and pull down. Where it is connected? It connects to header and processor. Okay. So what's so special about this pin? USB V bus. USB V bus. It connects here to this USB power and to expansion connector, and that's it. In the data sheet they say USB V bus. USB V bus monitors the presence of the USB bus power. We don't really need this feature, so we don't need to connect it to USB connector. But this is more interesting. A low level on this pin during reset starts the ISP command handler. That's what we need. We will use this. A high level during reset starts the USB device enumeration. This is the reason why there is pull up and pull down on this pin. By default, we need pull down the ISP. Have a look what is going to be after reset condition of the processor pin. If it's pull down or pull up. This is the processor. E23. E23. After reset, it says it is input. with pull down 100K. Perfect. And it's connected to NVCC EIM0. .3 volts. Perfect. Okay, this seems to be fine. So I just go through the pins. There are two things what you may be thinking about when we are speaking about this GPIO pin. The first thing is about the USB V-bus functionality. I know we said we are not going to use USB V-bus, but sometimes if you would like to reuse an existing software or firmware, and if they will be using this USB V-bus, you really still may want to be able to change the level on this pin. We can easily do that because in our schematic it is connected to processor GPIO pin, so if the USB firmware requires changing the level on the USB V-bus pin, we can do that through the processor and change it to low or high. The second thing what is important is what if someone sets the microcontroller pin as an output, and what if someone sets the processor pin as, you know what I'm going to say, as an output. We will have two outputs connected together. So if one of the output is high and the other one is low, they will be in conflict. The solution is, do you know what is the solution? The solution is set the pins, never set the pins as push-pull, but sets them as open collector or open drain output. In that case, you will need external or internal pull-up on the signal, and you need to play with the resistor configuration on the board. But don't forget about it. If you are connecting, because there will be the other pins which are connected to the processor, and for all the pins we always need to think how to set them correctly. So do not set two outputs together. GPIO1, exactly the kind of pin where you need to be careful. Do not set it as push-pull output, because the other side of this pin is connected to processor. I'm going to show you. Click here. It's connected to header, pull up and pull down, and processor. It's very important when you are browsing through your schematic, be aware where exactly or what exactly you have selected in this window here. Because if you are on the top of the hierarchy, like here, in this part of the window, you will see all the nets from whole schematic. So if you would be continuing and going through all the nets which are here, actually you would not only be checking this particular page, but you would be checking, you know, even the signals on other pages. You don't want to do that. So once you browse through the pages which you wanted to see, don't forget go back to the page which you are checking, and then continue in the list of the nets on the particular page. GPIO 0, very similar pin. Have a look where it is connected. It continues to the header, pull up, pull down, and processor. Always when you follow the signal, you need to go back to the signal which you are checking, back to this net. Do you know why? Because if I forget to go back, if I will be still here and I continue checking the signals in this window here, I would skip some of the signals because this signal is in completely different position in this window. This is the signal what we are checking, and this is where we are now. We skipped all these signals here. We didn't check this one. We didn't check this one. Okay, so I need to go back to the signal, original signal, which I started checking. I2C. There are three things what I will be looking for. First, if there is a pull-up on I2C signal. The second thing is I will be looking if data pins are connected to data pins and if clock pins are connected to clock pins. Sometimes happen that you may swap by accident these two net names or ports, and by accident you connect data signal to clock signal or clock signal to data signal. And the third thing what I will be looking at is if these two signals are connected to same I2C bus. I will show you. Watch. So this is I2C here. SDA, SDA, pull up, not fitted pull up. So we need to find where actually is a pull up, and it continues to SDA, 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 still no pull up. So we are going to look further. This is only connected here, and it continues here. Here is the pull up. So this is the pull up on the SDA, SDA, SDA pin. So this is important. You can see on this processor we have three I2C buses. I2C 1, 2, and 3. So when we will be checking the clock signal of the microcontroller, I2C clock signal of the microcontroller, it must be connected to this I2C 1 bus. So I2C 1 SDA. Where everywhere else it is connected. Here SDA, SDA, I2C 1 SDA, I2C 1, okay. I2C 1 SDA, I2C 1. We already checked this one. I2C 1 SDA, it's connected to SDA, I2C 1 SCL, okay. SDA, SDA, I2C 1, SDA, I2C 1 SCL. Perfect. SDA, SDA, I2C 1, I2C 1. Okay. Now I can go back to our microcontroller and check the clock signal. Same for the clock signal. If there is pull up and if they are all connected to clock pins. SCL, SCL, I2C1, I2C1. Not fitted pull up. So let's follow the signal. SCL. Oops, I need to go here on the top. Now I need to click here. Now I can browse the net. Perfect. SCL, SCL. Here is the pull-up. Perfect. I2C1, SCL on the processor. Perfect. I2C1, SCL, SCL. This is the header, processor, EEPROM memory, I2C1, SCL, I2C1, SCL, 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 I2C1, SCL, I2C1, I2C1, SCL, SCL. Okay, the I2C seems to be connected correctly. I can go back to our microcontroller page. What is next? Analog inputs. These are simple signals. It just goes to the header, and possibly we have option to measure the input voltage through this resistor divider. Other analog input only connected to the header. Oops. Another one only connected to header. Don't forget, again, you should be looking through the microcontroller datasheet and check every pin in the datasheet and in the reference schematic. Okay, just to make it a little bit faster, now I only go very simply through the other pins. This is a special pin because we use this pin also as this SWD high O signal, which is serial wire debug input output, which we would like to support. So we place that this switch, and if we need, we can switch between analog input from the header, or we can connect it to processor and control the signal from this GPIO on the processor. Okay, and this switch is controlled from processor to... Okay, let's go back where we finished. So this one is fine. This one goes to the header and to the switch or optional resistor if the switch is not used. 3.3 volt power supply. Okay, this one. For power supplies, I always go and found the source, the regulator in the schematic, because I've seen some cases when someone copied and pasted this page from a different schematic and the power supply net was called a little bit differently and it was connected nowhere, so there was no power supply. Let's have a look if we have this 3.3 volt LDO connected to a regulator. Here is the regulator. What you also need to be looking for is the maximum current from the regulator, which is 100 milliamps. That's not much. That's not really much. And this LDO is going to be used only in low power down mode, but we still need to check if the microcontroller can run even on the 100 milliamps. We can go to datasheet and we can find the current. Okay, supply current for the microcontroller. Be careful. The maximum current to the microcontroller depends also on the GPIO pins and how they are set. So this is just the basic current to the microcontroller, which is not really very high, maximum 40 milliamps. And for the output, standard output, high level current, 4 milliamps, low 4 milliamps. For this high drive output, that's something else, up to 20 milliamps. So in the low power mode, we need to be careful how the GPIO pins of this microcontroller will be set, but it still will work from these 100 milliamps, which are here. For the normal operation, we will use this 3.3 volt. The next one is reset output. We already checked this one. So I only go quickly through it. Okay. Reset output. In case we would like to reset the processor from the microcontroller, it goes to the main reset circuit of the board. .0 always. I'm not going to check this signal because we are going to change it. So I can skip it. LED 4, it's connected to resistor and LED, and it's also connected to processor GPIO pin and to the microcontroller GPIO pin. So what's important for this? Do not set these pins as output, set them as open collector, open drain outputs with a pull-up. So there is no conflict between processor and microcontroller. LED 3, exactly the same, connected to the processor and LED. Same. I'm checking these pins very quickly, but don't forget, you should go through every pin have a look into datasheet for the microcontroller, have a look into datasheet of the processor, and see if there are no special features of these pins or if there are no special requirements. I'm not doing it because it would take ages to record this video. No one would watch it. Maybe YouTube would cancel it, remove it, because it would say it's too long YouTube video. So this signal, we already checked this one. Again, very quickly. We also checked this one, connected to the processor. We also checked this one. Also this one. Oops. I always go back to microcontroller page. GPIO, again we check it. We checked this pin. GPIO 1. This is what I do for big schematics. I can be doing this like for 2 weeks, for example. Sometimes takes a long time. For simple schematics, you can have it in 1 hour, 2 hours, and you can save a lot of time, because I always, when I do this schematic checking, I always find something what needs to be fixed or what could be improved. And the best is if someone else is checking schematic after you, because then 2 different people have a look on it, and they may think a little bit differently and find the problems what the other person could miss. Okay. Serial port. What's very important for serial ports, for serial interface? Be sure you connect the transmit signal to the receive signal, okay? Because the microcontroller is going to communicate with the processor. On the processor, we have transmit data signal, which is connected to receive signal of the microcontroller. Sometimes you may want to also have a look if this really is input. So I go to the microcontroller and find RxD and check if it says it's input. Receiver input for the serial port. Okay, so we connect the transmit to the receiver input. You would be surprised, in some chips they actually say what should be, or they name the pin the way what should be connected there. They don't name it what the pin actually means. They name it what should be connected there. Have a look. Here is a CAN interface. This one. In this chip, they say here what should be connected there. Because if you have a look on this, you could see like this is TXD pin. It's not TXD pin. Here is datasheet. See? This is the chip. TXD. Transmit data input. So it's actually, it is not output, it is input. It is actually RxD pin. So always when you are connecting these kind of interfaces, be sure you check datasheet. I keep saying that, but you always need to check it. You always need to read the pin description, because sometimes some datasheets or some naming, it can really be confusing. RxD. So the processor receiver is connected to the transmit pin from the microcontroller. That's correct. SPI bus. What's important about the SPI bus? Let's have a look how it is connected. I will be looking if the MOSI and MISO signals are connected correctly. So this one is MOSI. MOSI, test point, MOSI, MOSI, and SPI flash, MOSI, slave input. That's correct. Master output, slave input. So if the processor is master, it will be output, and flash memory is slave, it will be input. Processor is master output, and the microcontroller will be slave input. MISO. So the microcontroller is slave output. MISO, and it's connected to the processor MISO. Processor will be master input, microcontroller slave output. Okay. The SPI flash is slave output, processor is master input, slave output. Okay. What you need to be careful about is the chip select for the SPI flash and for the microcontroller needs to be different. You can see, or you will see when we will be checking it. Here is the chip select. So the chip select 0 is connected to the microcontroller. Chip select, chip select, chip select, chip select 0, and that's it. If you have a look on the, I go back here so we can see on what chip select is the flash memory. The flash memory is on the chip select 2. Perfect. Also, what is important is to be sure they are all on the same SPI bus. Again, as for the I2C, you can have more SPI buses in one processor, for example. So all these, they are on SPI 3. SPI 3, 3, 3, 3, 3. SPI 3, 3, 3, 3, 3. Okay. If I go and have a look on the microcontroller, SPI 3, 3, 3, 3. Perfect. And the flash, SPI 3, 3, 3, 3. Perfect. We also checked the flash. Chip select, we check this one. Clock. Clock of the microcontroller is input. Clock of the processor will be always output. And normally we put series termination resistor on clock output or close to the clock output. So it's this one. And same clock will be connected also to the flash. In the final schematic, final OpenX schematic, you will see we made a little change here. We have there also option to disconnect the microcontroller from the SPI bus. You can check it by yourself on our imx6rex.com website. .3 volts. Pull up, diode, power pin for the switch. And also we need to check if this 3.3 volt is connected where. You already should know this. If it's connected to a regulator. So I go here and I'm going to check where is the regulator. I'm using arrow down and enter. Arrow down, enter. It's faster. Here is the regulator. Okay, this is the 3.3 volt source. It's connected correctly. And the ground. Okay, the coupling capacitors, ground, 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 ground. I look if there are two dots, and if there is only one, like here, zoom in and be sure this ground symbol is connected to pin. Sometimes may happen that this ground symbol is misplaced and it's not touching the pin. You would notice it when you are doing this kind of schematic checking. Perfect. It looks good. I hope you found this video useful. Thank you very much for watching. Don't forget to check out our other videos and see you soon.